So students, let us now see our next method, which is string constraint. So to understand this topic of string constraint, let us take example 26. So in our class notes, we have illustration 26, which depicts string constraint. So in example 26, we have a mass, let us say M1, and another mass here, let us say M2. So we have two masses, M1 and M2. And we have a pulley. So in between, I will make a pulley. So first of all, let me draw the table. So we have a table like this. Here also we have a table. Now, the ends of the table, we have a pulley. So one pulley is here. And another pulley is here. Let me draw the pulleys again. So this is pulley number 1 and this is pulley number 2. Okay. And these two pulleys are joined by a thread as shown. So these are the thread. Let us show the thread in red color. So this is thread 1 and this thread 1 goes down all the way. Here also we have a thread, another thread, let us say. And we have a pulley here. And this pulley is connected to a mass. Let us say M3 by a string. So this is the string which we have. So we have three masses, M1, M2, and M3. Now, we want to use string constraint here. We want to use string constraint. So let us first consider the accelerations as A1, A2, and A3 as shown in the diagram. Now, to apply string constraint, let us mark the length of the string. So let us say this is L1 length of the string. This is L2 length of the string. This is L3 length of the string. And finally, this is L4 length of the string. So this is all complete one string itself in red color. So this is one single string in red color all the way from here to here. So L1, L2, L3, and L4 are the lengths of sections of the string. So what we can say, because the string is inextensible, L1 plus L2 plus L3 plus L4 is constant. Now, if I consider differentiation of length, it will be velocity, and differentiation of velocity will be acceleration. So when we want to use this string constraint method, what is the process? Let us see. So for length L1, let us consider the endpoints. So these are the two endpoints of L1. At this endpoint, this mass M1 will move in the right direction. So the length of the string L1 will decrease. Because of the motion of this mass M1, the length L1 of the string, it will decrease. So in that case, we can say the acceleration value will be negative. So because the length is decreasing due to the acceleration of the mass in right direction, we can say minus A1. Why minus sign here? Because length is decreasing, length L1 is decreasing. So this 1 point we have written here. Now this pulley here is a fixed pulley because it is fixed to the table. This pulley is also fixed pulley. So these two pulleys, pulley 1 and pulley 2, they are fixed. Whereas this pulley 3 is movable. This is a movable pulley. So for length L1, one end is connected to this point. So minus A1 because length is decreasing. This point is fixed, so plus 0. Now for L2, let us consider for length L2. So for length L2, this is one point, this is another point. So this point is fixed, so 0. And this point here for length L2 is moving down with acceleration A3. So we can say that leads to increase in length of L2. So for L2, we can say the length increases due to acceleration A3. So plus A3. Why positive sign? Because positive sign denotes length L2 is increasing. Now let us consider section L3. So this point is moving down with acceleration A3, leading to increase in length of L3. So plus A3 again. Why plus? Because length L3 is increasing due to acceleration of block M3 and acceleration of pulley P3 in downward direction. Finally, this point here for length L3 is fixed. So this is connected to fixed pulley. So plus 0. Finally, length L4, let us consider. So L4, this point here is fixed. So because this point is fixed here, we can say 0 and plus this point. This point moves to left direction. So because it moves in left direction, acceleration A2 will come out to be negative because it leads to decrease in length. Now, finally, derivative of constant is 0. So we will equate this to 0. Derivative of constant is 0. So we will equate it to 0. So our equation for string constraint becomes 2A3 is equal to A1 plus A2. So this is the equation for string constraint. 2A3 is A1 plus A2. So this is how we will apply string constraint in this problem. So I hope the question 26 is clear. Let me show this method once again so that you understand it better. So let us consider again the same diagram. So let me come back to the same diagram. Let us see how we proceeded once again for length constraint. First of all, let me show the diagram. So here we have the diagram. We have three masses, M1, M2, and M3. Let me consider this length of string. So this is the full string in red color. Let us consider the various sections of the string as L1, L2, L3, and L4 respectively. So we can say by string constraint, L1 plus L2 plus L3 plus L4 is a constant. Now let us consider for length L1. For length L1, let us consider 2 points. One is this point here, another is this point here. This point is moving with acceleration A1 in right direction, leading to decrease of length. So decrease of length means minus A1. So because we have decrease of a length here, we will consider minus A1. Due to this acceleration A1 in right direction, length L1 decreases. So because length L1 decreases, we will consider here minus A1. Then this point here, this point is fixed pulley, connected to fixed pulley because this pulley is fixed. So we can say this point has 0 acceleration, so plus 0. Now let us think about L2. So for L2, we have 2 points. One is this point, another is this point. This point is connected to fixed pulley, so 0. This point is connected to mass M3, which is moving down with acceleration is 3. So this pulley here will move with acceleration A3 in downward direction. Because it leads to increase in length of L2. As mass moves downward, pulley moves downward, pulley P3 moves downward. So pulley moves downward, leading to increase in length of L2. So increase in length of L2. So we will write plus A3. Why plus? Because we have increase in length of L2 due to motion of A3 in downward direction. So I hope this is clear, this analysis. So now after this, let us consider length L3. So for L3, let us consider the points. This is one point, this is another point. This point is moving down with acceleration A3. So because it leads to increase in length of L3, because L3 length increases. So plus A3. And this point is fixed. So plus 0. Finally, this L4 length here. So L4, this point is fixed. So plus 0. And this point is moving with acceleration A2 in negative direction. And it leads to decrease in length L4. So there is a decrease in length of L4 due to the movement of mass in left direction. Decrease in length means we will have minus A2. Finally, derivative of constant is 0. So 0. So our equation becomes so we can say 2A3 is A1 plus A2. This is the equation of string constraint, and we have applied length constraint. So I hope you understood the method of length constraint. So let us move on to our next question. After this, let us go to next question, which is question 27. So on page number 48 of our class notes, we have question number 27, illustration 27. So in that illustration, we are given two pulleys. So let me draw the pulleys with a better diagram. So this is pulley number 1. And this pulley is connected to a mass. So let us first draw the string. I'm showing in red color. This is one side of the string. This is another side of the string. Now this left side is connected to a mass, let us say M1. And this other end of the string is connected to a pulley. Suppose we show the other pulley here like this. This is pulley 2. Okay. Now this pulley 2 is again connected by another string. So suppose we show another string here. And this another string is also connected to two masses. Let us say M2 and M3. So in all, we have three masses here. This is M1, this is M2, and this is M3. So I hope you saw the masses properly, M1, M2, and M3. So this is M2, and finally this is M3. So M1, M2, M3. Also, we have this pulley which is connected to a wall. Now, in this case, the question says, find the acceleration of M1 after the system is set free to move. So system is set free to move. We have to find acceleration of M1. Now, we can first apply length constraint here, L1 and L2, but it will not be useful. Why will it not be useful? Let us see. If I consider this red string here, and if I try to apply length constraint, what I will get? Effectively, I will get acceleration of M1 in upward direction is equal to acceleration of pulley P2 in downward direction. That is all that we will get. Acceleration of M1 in upward direction equals acceleration of pulley P2 in downward direction. Let us see if we really get this. Okay, so let us see how to use length constraints for M1 and pulley 2. So this is pulley 1 and this is pulley 2. Let us say we don't know what is the relation between acceleration of M1 and pulley 2. So let me consider acceleration of M1 is A1 and acceleration of pulley 2 is A2. So let us find the relation between A1 and A2 by using length constraint. So L1 plus L2 is constant. So let us consider the points. So this is one point, this is another point. So this point is moving upward with acceleration A1 because it leads to decrease in length of L1, because as M1 moves up with acceleration A1, L1 will decrease. So we will have minus A1. And this point here has zero acceleration because it is connected to fixed pulley, because pulley P1, it is a fixed pulley. It is connected to the wall, to the ceiling. Similarly, if I talk about length L2, so for L2 we have one point which is fixed, so zero acceleration. Another point which is connected to pulley P2. This pulley P2 downward motion leads to increase in length L2. So increase in length L2, so we can say plus A2. That equals derivative of constant which is 0. So from this we'll get the relation A1 is A2. And this is obvious. We already know A1 is A2 because the amount of length moved by M1 in upward direction equals the amount of length moved by P2 in downward direction. So this relation was obvious, but we still derived it by what? Length constraint. As I've told previously itself, this will not yield very useful result, but we just saw how to use length constraint if at all you want to use in this case. So by common sense, we can already predict acceleration of M1 and acceleration of P2, they will be same itself. So let us assume that by common sense itself, let us say this acceleration is A in upward direction and the acceleration of mass pulley or acceleration of pulley P2, it is in downward direction, which is A. Now, let us consider the acceleration of M2 here. Acceleration of M2, let us consider it is in upward direction relative to pulley P2. So let us say it has some acceleration A1 and this has acceleration A1 relative to the pulley. So A1 here is acceleration of M2 in upward direction relative to pulley P2 and A1 here is the acceleration of pulley mass M3 relative to pulley P2. So this is the diagram which we have. So now let us see how to use length constraint. So let us see the length constraint equation, what we will get here. So let us first draw the free body diagrams once again. Let us first concentrate on the free body diagram one by one. So for M1, we have one mass, one force which is in downward direction, which is M1G. Similarly, for M2G, we have downward direction. M3G, we have in downward direction. The tension force will be in upward direction here, and for these two masses as well. Now, we know tension in one string is constant. So let us say the red color string has tension T, whereas this another string here, which is in brown color, has tension T1 here. So T1 tension here, T1 tension here. Now, other than that, we have masses M1G in downward direction, M2G in downward direction, M3G in downward direction. So these are the accelerations of masses M1G, M2G, and M3G. Now, for mass M1, we have assumed, let us say, acceleration is A1 in upward direction. So pulley P2 has acceleration A1 in downward direction. Now of M2 and M3, let us consider M3 as heavy and its acceleration, let us say, is A3 and acceleration of M2, let us say, is A2. So acceleration of M2 I have considered A2, acceleration of M3 I have considered A3. So let us find the relation between A1, A2 and A3. So let us use string constraint method for the brown color string. So let us consider this length as L1, this length as L2. So again, I can say L1 plus L2 is constant for this brown colored string in down. So now, if I consider the points one by one. So for L1, these are the 2 points. So M2 mass here is moving in upward direction with acceleration A2. And it leads to decrease in length of L1. Because there is a decrease in length of L1, we can say minus A2. Similarly, this point here is connected to pulley and it is moving down with acceleration A1. So because this pulley P2 moves down, leads to decrease in length of L1. So we can say minus A1 because it leads to decrease in length of L1. Similarly, for length L2 here, this is one point which is moving down with acceleration A1. So this point is leading to decrease in length of L2. So minus A1. And this point here is going downward with acceleration A3, leading to increase in length of L2. So plus A3. Why plus here? Because as M3 moves down with acceleration A3, L2 increases. So this is equal to derivative of constant, which is 0. So our relation here will come out to be 2a1 equals a3 minus a2. So this is the equation for length constraint. 2a1 is equal to a3 minus a2. So I hope you understood this length constraint method here. So what we have marked, a1 is the acceleration of m1 in upward direction, and pulley P2, it is moving down with acceleration a1, and pulley mass m2, it has acceleration, let us say a2 in upward direction, and m3, let us say it is moving down acceleration a3. So this is the relation. So let me write this relation here. What is the relation which we derived? 2a1 is equal to a3 minus a2. Now, once you understand this length constraint, let us try to find the value of acceleration of m1, which is nothing but a1. So for that, let us use kinematic Newton's law equation. So let us see Newton's law equation one by one. So for m1, Newton's law equation will give us, for m1, we have big force minus small force is mass into acceleration. Big force is tension because it is in upward direction, and acceleration is also in upward direction. So T minus m1g is m1a, which corresponds to equation 1. For mass m2, Newton's law equation, big force minus small force gives mass into acceleration. So we get T1 minus m2g is m2a, corresponding to equation 2. Finally, for mass m3, we have m3g, the bigger force in downward direction, because acceleration of m3 is in downward direction. So m3g minus t1 equals m3a. This is equation 3. Finally, for pulley P2, we have two tensions. So let me draw the diagram of pulley P2. So one tension T in upward direction, two tensions T1 in downward direction, and acceleration of pulley in A1 in downward direction. So this is our free body diagram of the pulley. So if we want to write Newton's law equation, it will be 2T1, the greater downward force, minus T, the upward force, equals mass of pulley into acceleration A1. Now I consider the mass of pulley to be 0. In question, we are given the mass of pulley is 0. So we can say 2T1 minus T equals 0. So if I solve these four equations along with the equation for string constraint, I will get the value of acceleration A1. So how will we solve? I'll just give you an idea. You can do it yourself. So from this equation, I will find the value of, so first let us say this is A1 here. So this was A1. Okay. So M3G minus, so this was equal to M3A3. M3G minus T1 is M3A3. Okay. And for T2, we have T1 minus M2G is M2A2. Here we will have acceleration A2. Okay. So for M1, we have acceleration A1. For M2, we have acceleration A2. For M3, we have acceleration A3. Okay. So these are the three parameters which we have here. Let me write it in better handwriting. So this is A3 here, and this is A2 here. So how many equations do we have? So we have 1, 2, 3, 4, and fifth equation corresponding to string constraint. So in all, we have 5 equations. One equation for Newton's law for M1, another equation for Newton's law for M2, another equation for Newton's law for M3 mass, and fourth equation for Newton's law for pulley P2. And fifth equation we have by string constraint. 2A1 is A3 minus A2. So if I solve these 5 equations, how many unknowns do we have? T, T1, A1, A2, A3. So 5 unknowns and 5 equations. So we can solve them. So on solving, what we will get finally is, we will get the value of acceleration A1. So let me write the value of acceleration A1. So on solving these equations, A1 will come out to be 4 M2 M3G minus M1G bracket M2 plus M3, the whole upon 4 M2 M3 plus M1 bracket M2 plus M3. So this is the result which we wanted to prove, and this is what is the result we finally get. Now, how will we solve this? So let me give you an idea as well how to solve this equation. So from the first equation, we will substitute the value of t in equation 4 here. From second equation, I will substitute the value of t1 in fourth equation. So from those equations, I will get the value of relation between acceleration a1, a2, a3. Also, we will use this equation, fifth equation, 2a1 is equal to a3 minus a2. So on solving, we will get the value of acceleration a1. So this is the process by which we get the value of acceleration a1. Also, we can substitute the value of t1 in this equation also to get this for desired result. So this is how we apply string constraint in this case. So this is the equation of string constraint based on the direction of acceleration which I have chosen. If instead of acceleration a2 in upward direction, you can choose acceleration a2 in downward direction as well with respect to ground. So in that case, we will get another value of string constraint equation. So string constraint equation is based on the direction of acceleration that you choose. So this is perfectly right equation if I choose the acceleration in this direction and this direction as marked in the diagram. So I hope you understood this question. We move on to our next question based on string constraint, which is question number 28. So in question number 28, we are given a pulley mass diagram. So it is slightly a complicated diagram. So let me draw it for you. So there is one pulley and we have a thread or a string. Let me show it in brown color. So this is the string which I'm showing here. And the string is connected to a pulley on one side and another pulley on the other side. So let me show the pulley here. Let us consider first pulley as P1. So this is pulley P1. Okay. So here we have another pulley, let us say. So this is another pulley, let us say P2. So now let us show another thread here, another string in red color, let us say. So this is another string. In red color, I am showing it. Okay, so this is another string. And this another string is also connected to another mass here. And another string finally in, let us say, blue color. So let us show the masses one by one. So there is one mass here. Or let us say, let us draw this blue mass here. And another red mass here. So let us mark the ceiling. So this is the ceiling here. Now, supposingly this is called pulley number 1. This is called pulley number 2. And this is just pulley P. And here we have mass M1. And here in this we have mass M2. So in this case, again, we have to find the tension and acceleration. So we have to find the tension in the rope and acceleration of each mass. So let us first apply string constraint equation. So in this case, slightly I have drawn the diagram wrong. Let me just slightly correct it here. Let me rub this pulley. And let me rub this. Let me make slightly larger pulley. There's a slightly larger pulley here. And a slightly larger rope or a string. Like this. So this is one single string itself. So let us show that single string by same color, which is a red color. So let us consider length of the string as L1, L2, L3, and L4. So we have 4 lengths for one single string. This is one single string shown in red color. So we can write L1 plus L2 plus L3 plus L4. This equals a constant. And we have another string which is blue colored string. We don't want to use that. Okay. Let me show this string as well in another color. This string here. Let me show in some green color. Yes. And the ceiling is also in green color. Now, let us mark the accelerations one by one. Suppose we consider this M1 mass moves up with acceleration A1. And we can say if M1 moves up with acceleration A1, let us consider M2 moves down with acceleration A2. M2 is moving down with acceleration A2. So this pulley will also move down with acceleration A2. So for string constraint, also this pulley P1 is a movable pulley. So this pulley P1, let us say, is moving with acceleration AP1 in downward direction. And this pulley P2, let us say it is moving with acceleration AP2. Because this is acceleration of pulley, let us say we can use the symbol AP2 as well. So I can use AP1, AP2 as well as A2, whatever is convenient for you. Because this mass has acceleration A2, we can directly write A2 is also the acceleration of the pulley P2. Okay, so this is, let us say, A2 itself. Okay, so L1 length, let us apply string constraint now. So for L1, we have 2 points. One is this point, another is this point. So this point is moving up. This point is moving up with acceleration A1, leading to decrease in length of L1. So minus A1. This point is moving down, decrease in length of L1. So minus AP1. For L2, let us consider for L2. So we have 1 point here which is moving down, leading to decrease in length of L2. So minus AP1. Again, this point is moving down with acceleration A2, leading to increase in length of L2. Because as this point moves down, L2 length will increase. So plus A2 here we have. L3 length, we have this point here, which is moving down, leading to increase in length of L3. For L3, the length increases as this point moves down. So this point is leading to increase in length. So increase in length means plus A2. This point is connected to fixed pulley. So plus 0. Finally, for L4, this point is connected to fixed point. So 0. And this point is moving down with acceleration AP1, leading to increase in length of L4. So plus AP1. So that is equal to derivative of constant, which is 0. So our relation for string constraint, we will get this minus AP1 plus AP1 cancel. So we'll get 2A2 equals A1 plus AP1. So this is the equation for string constraint. So I hope now you understand the string constraint equation perfectly. Once you get the string constraint equation, Newton's law equation is easy itself. We have done it multiple times. So let us mark the forces. So M1G in downward direction, M2G in downward direction, tension T1 in upward direction. Here, tension T1 again here in upward direction. Here tension for pulley P2 is in downward direction. Here tension is in upward direction. Here tension is in upward direction. So let us consider the tension here as T1. The tension in one string is constant. So here also we will have T1 tension. Here also we will have T1 tension. And here also we will have T1 tension. Here we will have another tension T2. Here we will have another tension T2. Another mass M2G. Here another mass M1G. So for this free body diagram of M1, we will have Newton's law equation as T1 minus M1G is M1A1. So this is the equation of Newton's law. For mass M2, what will be the equation of Newton's law? It will be M2G minus T2 is equal to M2A2. So this is Newton's law equation for M2. Finally, for pulleys, so for this pulley, we have tension here as, let us think about the tensions here. So for this pulley, we have 2T1 upward force is equal to T2, which is the downward force. So in all, we have 4 equations now. one equation, two equation, three equation, and four equation. Here we have four unknowns, T1, T2, A1, A2. So four equations, four unknowns, it is sufficient. So we can get the value of T, tension T1, T2, A1, and A2 by solving these four equations simultaneously. So I hope you understood this completely now. Okay. So we have in this case, let us consider for this pulley we have tension T1, T1, and here T2. So we have T2, T1 equals T2, which is the equation for this pulley. For this equation here, we will have some mass of pulley because here we have tension T1, which is same all throughout. So T1 in upward direction, to T1 in downward direction. So there should be some mass of this pulley. Okay. So that is how we'll solve this question by length constraint equation. So I hope it is clear how we solve this by length constraint. So let us move on to next question, which is question number 29. Now, before moving to question 29, we have to learn a concept which is called as wedge constraint. So we will learn what is wedge constraint first.